Here on my computer, it's 10 o'clock. So I hope you all are having a great day. Before we get started, a little bit of housekeeping here. As you know, we are recording this, but only us and our slides, not your names, not your comments, nothing. We have a couple of polls prepared where you can anonymously just say what is most relevant for you. And yeah, I'm looking forward to a very interactive webinar today. Stay tuned if you want to see something about how experts use EBSILON, what EBSILON can do, what latest features we have, what this urban quarter project really was, what was the technology behind it, what was the project approach, what was the background, the technical background. We will all address that here in the next hour. And with the feedback that we get from you in the polls, we will try to make it as appropriate and fit for you as possible. So please make use of that. Give us questions or hints in the chat if you have any ideas. So let me show you the agenda and let me introduce my colleagues here. Maybe that first. Let's start with Tobias. Good morning, Tobias. Thank you for joining. Hi.
Hi.
You are, I checked it, Tobias, already 15 years with STEAG, as I can see. And currently you are system architect and development manager for EBSILON in Zwingenberg, in our beautiful subsidiary in Zwingenberg. So hope to have the possibility to visit all of you soon again there. And from the other colleague here, Florian, Dr. Florian Dauber.
Good morning, everybody.
10 years and 1 month. I just checked it yesterday. So that went very fast. So let's look at what projects you've seen in the meantime, what experiences you have. And I think your EBSILON background goes even further, right? University?
Yeah, you name it. Actually, I had my first contact to EBSILON as a simulation tool during my time at the university, where I had actually learned with EBSILON how to simulate processes all over in the energy world. But as I got promoted into working at the university as an assistant, I actually was on the other side of the table, so I can teach EBSILON to younger students and to upcoming talents, which we then integrated into STEAG from time to time.
That's true. Yeah, we have some of the colleagues that did the thesis. They decided to stay with us for longer. So that's a good sign, I would say, that everything is going well. So, okay, let's quickly have a look at the agenda here, and we will be back soon with you two and a couple of practical examples. So those are the slides. I will keep that super brief. And now what we see now, a couple of you joined last month already, but I will keep it even shorter this time. Just for those that joined for the first time, it's important to see it's not just software that Tobias and Florian and I just thought about yesterday. This is engineering. This is 20 years of experience for the development, sometimes even more. So yeah, let's have a quick look here, and then we can go really into the what it all is. And we even have a little challenge here today with Florian, who holds the official world record for the fastest EBSILON model that can calculate. We will be there in like 10 minutes from now. Very, very briefly, STEAG, for those that don't know us, we are an international company. We are an energy company. We have more than 6,000 employees worldwide. More than 100 gigawatts of power plants around the globe use our digital solutions. We will see what that is also in a minute from now. We have more than 11 gigawatts of installed capacity around the globe with operation and maintenance contracts, where we as STEAG develop and optimize the operation and maintenance constantly. And you can see Europe, Middle East, India, Southeast Asia, and China, very international project background. And so that is very helpful for us. We can do many things from remote. This is even in those times as today, very, very helpful to be flexible and you don't have to go somewhere and be personally on site. That is very helpful. But very briefly, those projects, applications that we can do with those things that we will look at today. EBSILON is today the main topic, of course, but EBSILON is part of a product family. And here we can see a couple of examples about that. Here, the boiler cleaning management for power plants, 66 gigawatts, but that currently use our EBSILON-based system there. They are using that for cleaning optimization, for efficiency optimization there. Also here, that is also the 82 gigawatts process and performance monitoring is also driven by EBSILON. And of course, there's also other modules, other ways to process data that do not need EBSILON. But this is all part of one family. And if you have one thing, you can easily upgrade to another thing if you need it as well. So what are our digital solutions? It's always the owner's perspective, or operation and maintenance, best practices, and cutting-edge digital systems. More than 250 units use it. I'm saying that because since it's so many projects, we can take the effort, the extra mile to make it easier. That's also what Tobias will share with us today. There was one project, one Florian that had one question, but still we would do it like a solution that is long-lasting and also flexible for other things, since we have so many projects where it makes sense.
But that is,
please,
maybe just to add to this,
please.
I think what is special about STEAG is that we actually can deliver to all of those three aspects. We have the owner's perspective, we have the best practice for O&M, and we have the digital systems with a background of over 20 years. So having all those three parts covered in one company, I think this is unique.
Absolutely. And that is closely integrated. I think that's also good. Yeah, that we work together, we have projects together within the company. So that is, I think that's a very strong point of us. Absolutely. Thanks. Yeah. Oh yeah. So that is all aimed to maximize availability of assets, to improve the plant load factor and efficiency, to reduce maintenance costs and avoid unplanned outages. So always, yeah, the owner's perspective on the asset, that is what we are standing for and what we are working on constantly. A final slide here about our asset intelligence framework. At the bottom, we have different software modules. We have experience in different fields in the middle. And the most important part for us is to really have all that, but know how to integrate that into the real world at the customer's side. Yeah, if you get 200 alarms from a system a day, yeah, it's not helpful for you. What we need is very reliable information, early on the information, transparent information, so that can be turned into insights and actions. Yeah, that is, it has to be actionable. Everything else is not so helpful. I would like to finish that little introduction here with a couple of numbers taken from those projects where EBSILON is taking a crucial role in many cases. So by finding, for example, unit heat rate optimization in an 800 megawatts coal-fired plant, that first bubble, that saves over 8,000 euros per day constantly, since it was found, and it wouldn't have been found without such a good tool. Or another example, let's say 70,000 euros saved because we found unintended vibrations. That was, of course, based on the SPC, Statistical Process Control module. But those are all examples, and they all show us payback period in most cases is below 1.5 years. So if that's interesting for you, make sure to reach out, and we can have a private meeting afterwards to see if those modules and which ones deliver the most value for you and your problems and challenges. Good. So before we finish, for talking about EBSILON for 10 minutes already, but what is it? It's a software. You can buy it. It's a CD. It's much more, but let's keep it simple for now. We see a standardized model, and we will have the challenge with Florian in a second here. It's the market leader in Germany and even further. It's very flexible, user-friendly. We also offer professional services. We offer trainings and workshops, and it's not a black box. So a customer that has a project with us and has an EBSILON can open the model and use it in the future, make some changes on their own, or, you know, that it's really open, it's really transparent. And as I said, more than 20 years of constant improvements. I remember 10 years ago, we were working on solar thermal extensions there. That is, Tobias will share a little bit how EBSILON evolved over time, and that by now we can even have PV and wind in a model to a certain degree. So that is very strong. And let's see. So, yep, that's it. So for now, before I finish that part, I would like to ask you all one question first. So we have 5 questions in total. Last one is only if we have enough time. So I would like to ask you, where are you coming from? What background? Are you more coming from the renewable industry, from the thermal plants? Are you coming from waste to energy or education? Let's just make it quick, 10 seconds here. Yeah, education, thermal, very good. So yeah, Tobias, Florian, if we have examples, maybe we can focus on those things. More clicks are coming in, great. Other, okay. If you want to share what other is, just leave us like one bullet point in the chat and we will know. Good, lots of thermal as well, good. thank you all. I think that is helpful. Yeah, we want to interact with you, so that is a great way to know who's attending today. So let's present the results, and here we go. Today, most is thermal, but also education and other. So great. So thank you for that. Now I would like to talk about latest projects and today's agenda. Let's look at this, that we can use that for the next short discussion here. We have different things today on the agenda. So what is most interesting to you by what you hear about that, the urban quarter optimization for sure. Florian, we will talk about how that project in detail. Also, we prepared the energy island, where we will show some isolated examples. That can be an island, but that can also be in a country, a region that has maybe a very weak connection. So we have what else? Capabilities and smart use of EBSILON in general. Yeah, that's also something that we want to see. How do you approach such a task, and how do you solve it? And yeah, great. So what I will show it to you. Okay, great. Okay, so half of the audience would like to see how to use EBSILON like a pro, and the good news is that is the right bunch of experts here that we need. And so let's get going here. Okay, now next one, and that is maybe we can use that as the agenda now. I introduced you both very briefly, and let's not make it too long, but maybe focus a little bit on what you've been doing for the last years. So I have a couple of buzzwords here. Maybe Florian, you could start, share a little bit what you are doing recently, what is connected to EBSILON, what not. Just a short overview for the people so they know who's here today and where it's coming from. And the audience can click what is most important for you, and we can then finally get going here and really go into the details. So maybe Florian, just those first points, what is your pitch there?
All right. So what I've been doing in the latest in Steag is I work mainly with those digital solutions you just presented. So I was very active as a project manager for process monitoring, especially in coal-fired power plant in the last couple of years. Then I managed, and this is what I'm actually doing right now, is an urban quarter solution for a customer where we build up a huge EBSILON model for exactly planning the grid of an urban quarter and have a deep dive into the energy generation there. I think we will talk about this later on in this session today. And what I'm doing as well, and where I focus mainly in, is that we actually build up a platform right now, a smart cloud-based asset management platform for renewable energies. That those tools you just mentioned, the anomaly detection or the digital twin, big data solutions, that those tools and solutions are offered even for renewable energy sector more and more, and even for smaller plants. And this we'll do with the help of a platform that I'm building up right now. It's really challenging, but very, very interesting project.
And let's make sure, if that is at a certain point, we will also have a web seminar about that and share those insights. Maybe,
most def,
as soon as possible. Great. So maybe Tobias, you want to say a couple of words to those things? I think I can already see. Maybe we share it now, and you can see what the people are interested in. I think that's great.
Yeah.
Look at that. Wow.
Yeah. So it's quite a wide range people are interested in, and that's a cool thing, because we can do all of this with EBSILON. Of course, some things you do on your desktop, other things you do when EBSILON is running in the backend as a service. So that's in the end what I've done for the last over 20 years, because I'm already developing EBSILON for over 20 years now. And the last years, we deeply invested into getting in stationary EBSILON calculations running, because that's a pretty hard thing to do, but it's necessary for today's especially coal-fired plants who going up and down all the time, and we don't have like driving the line only. And yeah, so we can show you a lot of solutions, and also we have this small solution for energy islands where we have all the different power sources, and EBSILON calculates or can show you if your power sources are enough for your island, or you have to install some additional firing or motor engine to back up in
Great. Yeah, I think that's the main point, the method that we have here. It's very versatile, very different technologies that we can incorporate there. And yeah, when it makes sense and how to do it, that is something that is even part of the service contract, where people can just call, hey, I want to have a battery in my model. I know it doesn't make thermodynamical sense, but is it possible, and how? And we will help the people to use it efficiently. So great. So I have one last poll before we really go into the EBSILON there. And that is number 4, start. So because we want to focus on what you want to know and not bore you with boring stuff that you already know, maybe you can quickly click on how much EBSILON you know. Maybe you are a veteran there, you use it for many years, then of course you want to know something else, and somebody who's totally new here or maybe comes from a business background, I don't know, yeah, oh yeah, it's coming in. Thank you all for participating. That really makes it more lively here. Let's give it another 5 seconds and then we can have a look. But yeah, okay, great. How to accommodate all this. Yeah, it is not easy, but it's good to know who's participating. I think we will close it for now. Thank you. Look at this. Wow, that's a very mixed audience, but I think we can make it. So maybe if it gets too complicated at the end, that is something that takes some training, some experience there. But what Florian will show us now can be learned within an hour, and that is part of the standard basic training that every customer receives when they get this kind of EBSILON package there. So let's go out of here. Let's go back to the cameras, and yeah, Florian, maybe now I may challenge you to show us that you really earn your world record in the fastest EBSILON model in the world. Not fastest calculating one, but fastest assembly one. It's a little bit small for everybody, but don't worry, it's just about the big picture. So yeah, Florian, the time goes from now. You can just click, and I will do a little bit of the comment here. We see the EBSILON Professional. We see a couple of working fields. Florian can now go to some predefined components. There's more than 150, 180, something like that. So like a pipe, a pump is a component there. And Florian will just put it together now and make an easy water steam cycle.
You start the clock?
Okay, I will do it. Let's look at the watch. Okay, please go now. Good.
Oh no.
See, a boiler component. We connect those pipes afterwards. Turbine, condenser. Okay, a pump. Now we connect the pipes. EBSILON will help as much as possible. Every component comes with a standard characteristic curve. In the project, Florian, of course, would spend lots of effort to really tailor that to the current situation there. This calculation needs some input values, so temperatures, pressures. Some stuff comes from another component, but yeah, of course, Florian knows here what to plug in.
Oops.
I can challenge you, if you in the audience can do it faster, we might even, have a trophy there. Send me a video that proves that you can do it faster than Florian, and we will think about something there. I think he's already done going for calculation soon. Okay,
yeah,
good.
Now.
Okay,
yay.
So that's it. Here it was roughly a minute because I didn't use the stopwatch today. But Florian, that was a good job.
Thanks.
So why did we do that? To show you how easy it can be. Yeah, that is what you want to do. You want to change the temperature. You immediately get results. You can see, how much electricity you make, how much heat you produce. Now you can put in, I don't know, reverse osmosis. You can put in a gas engine and so on. That is all building up now the model, but you see how easy it can be. And so maybe now it's time for Tobias to pick it up there and show us, yeah, that was easy. What is even possible more, and what are new features there? So maybe Florian can stop and Tobias can share. And good news is we are very good in time for those things that we want to address today. We are just right in time so far. So we can take 5 minutes easily for the EBSILON now.
I think, Florian, you have to stop sharing.
All right.
Please. And you already see how difficult or how complicated it can get here.
From an easy Clausius Rankine first principle model up to a detailed hard coal fired power plant. All right.
Florian, the detailed one is also 1 minute, or does it take longer?
No, I just hand over to Tobias.
Yeah.
Okay. So what I want to show to you is if you spend a little bit more effort into modeling, you can end up with models like this. This is an example model which is distributed with a DVD, and it shows more or less standard coal-fired plant with roughly 700, 500 megawatts of power generated, and you can run it here and it calculates within 30 milliseconds. You have the whole model calculated, and you can drag the mouse over and get all the values on the streams and also values from the components. And if you want to have more detailed information, you can either plug in like value fields here, which you can specify by your own, and you can also get into the streams and look at the detailed result values and also the composition, which is not so interesting for water, but gets more interesting when you have like air or flue gas lines. And of course, you can also look into the components and see specification and result values for each component. Okay, and of course, what we else have is we have like a design mode where you can specify the components and you get a layout of your model, and you can also go into off-design calculations where you like drop down the mass flow in this model, and we have like characteristic lines for adaptation of the components. And now I can drive this model at 90% of load, and I get a reduced power output now of only 700. Okay, let's make this here. Okay, we see 733 megawatts only. Yeah, and that's roughly a model to play around with. If you want to be more complicated, or we have like a configurator for gas turbine models, which is quite elaborated. You can click a model, a complete gas turbine model, faster than Florian did his simple model. And I take here the gas turbine. I take an HRSG with three pressure stages, and I put in a steam turbine system, also like with 3 stages, and I put it here. And now I only press a single button. I have to find up here, or here it is, and we get all the lines, and it's already calculating. And we can also add an additional cooling system. Let's take an air-cooled condenser also and put it also, I'm not sure where to put it right now. Let's put it here, and again, click on the connectors, and it's also calculating already. And of course, those are not black boxes. Those are called macros, and macros are like part models to give you a better overview of your model, and you can step inside and see this is the HRSG that's really calculated. So EBSILON is not abstracting away, and you only have like a characteristic line-based model. No, it calculates the whole stream, the flue gas stream going through all this heat exchangers, and that's all calculated. So for the calculation kernel doesn't know about macros. It sees always the whole model and makes the balance over the whole model. Okay, so much for our configurator. And then there is the island model. Here we can show that we also have like a time series calculation, and I take here we have a 5-minute based time series with wind and solar data over 1 day in 2019 on some island in, I think, in the Indian Ocean. And in the model, we have a wind turbine, which produces current when the wind is blowing. We have also a photovoltaic system in here. And we have a final backup, a water storage, which has like 2 tanks, and the upper tank has 49 bars more than the lower tank. So we have a pressure drop, and we can produce power from that. And in case we still need, we have a primary backup, which is a battery down here. And in case we produce too much power, we will load the battery or pump up water. And in case power is missing, it goes the other way. And now we can simply calculate the whole system. I go into the profile for the calculation, and now we run the whole day. You see the clock is spinning around, and the battery is loading and unloading. And when the battery is finally full, the tank gets pumped up again, and and now we're already through. And now we've calculated a whole day in 5-minute steps for the island, and all the intermediate data. So you can go to each point in time and calculate it and recalculate it manually and inspect it in case you had errors or So you can do a detailed engineering of the whole model.
Great.
Okay, and if I've got 2 more minutes, I would finally like to show our interfaces. So, okay, on the one hand side, we have an internal interface, which is our EBScript language, which is a Pascal-based language. And here we have a very small script, which simply calculates all the profiles in the model, and which already happened. But we also have, you can have arbitrary complex scripts, which I think Florian will also show you right now. And here we have a script which analyzes the topology of the model and prints out information about which component is connected to which other component. So
great.
And also on the outer side, we have a very elaborated automation interface for EBSILON based on Windows COM technology. And on the one hand, we have this Excel add-in, which is provided by a company from Austria, which we work close together. And here I also use the same model I just showed you, and I can run the different profiles, and I did just 4 calculations in EBSILON and got back the results. And I can also put in additional specification values. Now I can override the more or less the load of the model, because I know at full load it has roughly 600 kilograms per second. But if I specify 500 here, I should get a higher produced generator power now at almost 700 megawatts. And you can have arbitrary large Excel sheets, and people do that. And finally, I would like to show our which drives all this, because it's more or less Excel VBA, or you can also use it in C#.NET or also from C++. And this is, here we have like a little bit of VBA code, which uses this apps open interface. This is a driving interface, and we start always up with the application, and we open models, and we get back a model, and then we can access the objects of the model and run simulation. Here we have the simulate routine, and you can access more or less every data point in EBSILON and read or write data to it. You can generate new profiles in the model and do what-if simulations and all kind of stuff. And I know that our SR EPOS systems are heavily using that interface.
Of course, yeah. And now everybody knows why we showed the easy example before. It can get very difficult pretty fast, but of course you are invited in the training. You say, well, I have this thing in my mind. I want to do this kind of calculation. What do I need? Should I just use Epsilon like that? Should I use Excel interface? Should I use time series? We can help you as part of the service contract there to really save you much time, to really go right for the right approach, because we have this background. We know where Epsilon, is very strong, or something might be very difficult because you do very complicated thermodynamical things. We can advise you and help you to really save time. Yeah. So great.
And one final remark, you can use the scripting engine to do like visual helpings, because this is what a colleague of mine did. He did a coloring of the model depending on the temperature, or coloring of the stream. So when you switch to different profiles, I hope there would be more profiles right now, but you can see on the color of the stream its temperature, or you can estimate it at least. And yeah.
Great.
Okay.
Wow, okay. Thank you. That's good.
Okay.
Quick welcome to those who just joined. We also have a recording later on that we can share with you all, so you can catch up to those things that you missed. Now let us go to the urban quarter. Let us now go to the urban quarter example. And Florian, if you don't mind, I will give a quick overview, and then you can really go into detail there. But I think it's important to see what the scope was and why that was a difficult thing, and why you would ask Tobias and his colleagues for advice there. So the use case of the urban quarter is our main topic of today, but now we have the groundwork done to see what that is. Yeah, we cannot talk about the optimization without talking about Epsilon and the components first. This project, Florian, it encompasses combined heat and power. It was supposed to be a climate neutral urban development, something new, where in the past something old has been. Yeah, so very future, very much looking in the current requirements there. More than 200 house connection stations were required. So, like not a house, not a one family house, but maybe a industry building, a big office building. They need heat, they need power, they need cooling in summertime. And that was all supposed to be optimized over summer. Yeah, the scope, we have it. The technical details to give you more understanding what that meant. We had the distribution network to be modeled, plus the central producers, and those were a combined heat and power unit, heat pumps that used air or geothermal energy or water to water, so to get this heat out of the environment. A gas boiler, storage, so that is Tobias, where we saw your storage tanks and so on, where this can be helpful, I think. And of course, the decentralized house connection stations, so very prosumer oriented. Yeah, people can not only consume from the grid, but also put something back. And I think that is really where the whole development goes currently, that it's getting much more complicated than it was in the past. The goal was to have an hourly annual simulation. So, like every hour, one result, maybe this is time series that we saw from Tobias just now. They wanted to have a selectable sequence of use of the producers, and they wanted to record the primary energy factor and CO2 emissions according to the guideline. So that sounds simple, but I think that's a lot of thinking necessary to deliver that. To optimize, it was supposed to be looking at generation, storage, and flexible consumers. And we will see mathematical optimization that was done with regard to economy, partial load behavior, security of supply, stability and sustainability, and finally, determination of the annual energy balances. We had the efficiencies calculated there, the load behavior of the network and the components. And finally, it was a holistic design, one model for all of those different things, that because for those results, they have to all be considered there, plus future decision support, how to expand, because they knew already the first stage will not be the last one. How can they use that in the future? So yeah, finally, what can we optimize? Yeah, because they also want to put the merit order approach there, to save money also in getting that energy that was needed. So that was looking at the producers, the storage, and the flexible consumers once again. And I would like to finish with this picture here. It was user-friendly because it could also use the gas turbine library. It could also use the reciprocating engine library. That is all what Tobias mentioned from Anexa in Austria, standardized modules that we can use there. And finally, part of the development of that project, house connection stations configurator and a library. So you added a feature there to have it easier during the project and in the future. I think that is very impressive. So yeah, let's finish here and go into the more detailed view with Florian. Annual energy balances were created, efficiencies, load behavior, a test series was created. Yeah, how to continue on that journey for the customer. There was this project. There was a plausibility check and validation of the results. Highly transparent and traceable results, because yeah, there will be questions now, and now they can just use EBSILON and answer them, what was used, what measurement, what tag, I don't know. Very, very transparent. And last thing, the customer can use the model on their own afterwards. Now, after we saw from Tobias the scripting and everything, you can set it up so nobody, maybe not even yourself, is able to use it in the future, or you make it in a structured way, and customers, colleagues, and future users is ensured. So Florian, that is maybe the point to jump back to you, and you can show us more how that looked, yeah, from your perspective. We will have a two-step approach here. Florian will tell us the project demands, and then we will look at Tobias to say what was this for the developers, what was there on the table to solve. So Florian, maybe after my general overview, you could point out a little bit, yeah, what was really the need and how would you approach that in EBSILON?
Yeah, I think what you just described very, very fast, I guess, like took us like roughly a year to accomplish. But you got to understand at this point that urban quarters, especially those energy concepts, are quite complex, as you have to figure out, or you have to model a certain number of completely different technologies. As you just quickly mentioned, you have heat pumps, you have combined heat and power machines, you have gas boilers, we have solars, and so on and so far. Even geothermal storage devices were to use. And I think this plays into the hand of EBSILON, as we have a tool where you can model and simulate all those technologies from one source. You don't have to switch between different IT solutions. You don't have to use Excel for model a quite complex energy solution. And therefore, I think it's really handy to have a tool which is not specialized just on one technology, but you have the possibility to model the whole complex grid and the house connection station, and even the energy generation in one tool. So having it in one model, you can change on one end and you see the effects on the other end, especially when you are concentrated in CO2 emissions or in the primary energy factor. It's very, very important that you have a holistic approach and you have an overview of the whole generation station. Yeah. And another thing which was really, really important in this project is having the possibility to or have an access to different fluid model, to different thermodynamic equations of states of different mixtures, as Tobias just mentioned. We have a lot of different.
Show it on the screen what kind of things we have. Could you quickly find that just to show this list?
Yeah, especially yeah.
I think that is very helpful.
I step back here. For example, if you we have natural gas, we have oil, we have flue gas, we have air, we have water. All those mixtures or fluids use different thermodynamic equations, and to be able to set up your own mixture is really important in here, right?
Right. I think the precision of your results will largely depend on that, and maybe also on the characteristic lines that you can use for the modeling.
Yeah, you name it. Exactly. Always the goal is to, if you want to come as close to the reality as possible, you definitely need, good thermodynamic equations, but you also need manufacturer data, having the possibility to add the design data of the actual equipment into the model. I think EBSILON is helping you in this case as well.
Maybe we could have a quick look at one example here, exactly like maybe a heat pump or something, just to have it a little bit more transparent.
Yeah. I think what was interesting in this project right here was the customer is using combined heat and power engines, right? And it is not always simple to get access to manufacturer data, as you probably all know in the audience from your own projects. And here we have the chance to have access to a library of manufacturer data. So you can see you have data from Caterpillar, Jenbacher, Kawasaki, MAN, and so on and so on. So you have detailed design data of gas engines. And so you don't have to figure out those numbers yourself or get in time-intensive discussions with your manufacturer. And I think in order to get it as close to the reality as possible, that helped me at least a lot during this project.
Florian, I have to
maybe
a little bit, so maybe we can have like the problem now where you went to Tobias and his colleagues soon, because I don't want to run out of time, you know.
Yeah, sure. Sorry, what was the question?
Yeah, like we have to finish that part pretty soon, so maybe you
All
can
right.
show now where the difficulty was. Where did you ask for help and why? So Tobias can take over. I could spend an hour on that. I mean, I like it myself, but we have to make sure to finish on time.
It's okay. I think one thing we learned today is that actually EBSILON can be really easy to start with in the beginning, but you can get into very much detail, right? It can get complex. For example, this was the grid of my urban quarter solutions. And if I click into the energy station, you see all those different energy producers. And even there you can go into detail and see, like, what does the heat pump look like? What does my combined heat and power look like? And the goal in this project was to get it as user-friendly as possible, right? To get a customer on the other side who has to work with this simulation every day to get him, to make it as user-friendly as possible. We've done this via like those macros where he can choose his own merit order, right? This is the order in which each producer of energy is selected. But yeah, I think this is a point where I actually contacted Tobias for help. Tobias, please help me get it as generic, as user-friendly as possible, so that even like amateurs have a chance to work with this specific model.
Yeah. Okay. May I come in here? So the idea was to not only have the code, the app script code that Florian uses to do this, and not written in each component for its own, but to have it written at a central point, which is possible in EBSILON. We have Pascal units. People who know Pascal maybe know. A unit is like a function library, which you can use in other app script components. And we put it in the model, and the components, the single macros only dispatch their calls to this centralized code and just plug in their numbers. So they plug in the merit order or the number of this access points that are currently in use, and the centralized code is able to do it in a generic way, because it only has to know the numbers and some of its configuration data to do the whole calculation. So we abstracted away the concrete instance and had a generic model, which is easier to maintain because we only have the code at one point. And when you make changes, you don't have to redo your changes in each component. And on the other hand, it's much easier to simply test something new, because you only change it at that single point, and you know now it's running in the changed way in each of the components, and you can run your tests and say, okay, it works, or no, I have to undo it. And I think that's really speeded up your way of doing the model, or of working with your model. And today it's also used by the end user, because they can easily change the merit order or change the number of houses attached to a stream.
Exactly.
Okay.
This grid can grow, or the model was built up so that even when the grid is growing, where more energy producers or machines are added, it's simply for the user to enlarge his model himself.
Yeah, I'm glad. Yeah, if I imagine that every component would have some individual settings, it will be very hard to maintain it over time. And if different people use it, if you do it yourself, you might know where to go. But if different people do it, you are lost at some point. So that was a good approach. Is there anything you want to show, Tobias, for a second there? Is there anything, I don't know, that is worth showing?
Maybe Florian can show some of the code.
Okay, great. Yeah.
Are you able?
I think you're still connected, right?
I don't know whether I would show the code, but
okay, yeah, maybe some of the more details of the access points, the home access points.
Yeah, if this is what the grid looks like. And what I was just talking about is how the customer is enabled to modify the grid himself. And for example, if I go to one grid section, which is one part of the huge urban quarter we are talking about, can easily enter the numbers of different house connections at this point. Each one of this stands for a different type of house connection station. Whether this one is quite a big company building, this is like a family house, and this is an industry building. So you can add the number, and each one is connected to a library that we build up during this project for 13 house connection stations. And each one is now able to be calculated over a whole year. The aim at this point in the project was to find the right dimension of the pumps, the right size and number of the energy producers, so that even during really, how to say, days with special climate conditions, really hot days during summers, or even very cold days in winter, you have to make sure in advance via such a model whether you equipped on the right scale, right? So you don't. We make sure nobody runs out of heating during hard winter days.
Good. I could think about a couple of international applications there where that could be handy. Yeah. Great. Well, once again, I think there was a very good deep dive here, and half of the audience asked for that today. The other half might just be a little lost by now, but that is not a problem. We can have that always in the chat afterwards. I can see a question here. Let's see, Florian, what is the hardware configuration on which the urban quarter model runs? Oh, I think maybe that's, do you mean server-wise, like how many CPUs, or do you mean like grids and connectors? Maybe you could specify. There's a question in the chat for the moderators.
I think I rather think that's going to the computer. Yeah, the computer hardware. So Epsilon usually runs on your desktop PC. Of course, you can run it on a multi-core server, and they benefit from the multi-cores. But a model like Florian's can definitely run on a laptop, and you don't have. You may be a bit slower, but only in the percentage area than on a server, because the calculation of a single model usually runs faster when it's run sequential. We have multi-core support, but that usually only benefits when you have really the hard fluids. Like we have also fluid property libraries from NIST in the US, or from universities in Germany that have really elaborated first principle fluid property libraries, which have very hard computations. And so when you run those fluids, you benefit from multi-core systems. Or when you run really, really large models, we have models with over 4,000 components, and those benefits, and they still run on my laptop, and they run fast.
Maybe I can add here and answer Rajbam's question as well. Is if I pick out one single moment, one simulation, it takes me less than 5 seconds to solve like this point in time. If I calculate a whole time series with this really top-notch, quite complex model, it takes me like for, let's say, 5 hours to calculate 8,670 hours per year. So to calculate a whole year, right?
Great. Well, yeah, I think maybe we think too complicated here. Most people would say it's pretty fast, the Epsilon. It even works on regular computers. And yeah, but it was a great question. Thank you.
And we're running on very high accuracy in our models.
But coming to accuracy of timely finish, Tobias, I was relaxed because you already showed maybe half of the energy island in the first one with Epsilon. If we could take 5 minutes now to show a little bit more of this energy island here, and after the full hour, we can of course have more questions afterwards. But let's have this, and then because we have 8 minutes remaining, and you know, that is better for those that have appointments afterwards. So okay, now right back to the energy island thing. Yeah, like isolated things that are similar to the urban quarter. That's why we put it together here. Different things, storage in one isolated grid, where you cannot always say, well, I just buy it from the grid. So Tobias has a couple of running models here for us, and you can see the storage here, for example, on the right hand side. You can see over time how that works. So stage is yours, Tobias. Thank you.
Okay, so
Tobias, just quickly explain why it's an island, and where is this island actually?
So why is it an island? Because we wanted to show that Epsilon is capable of doing an energy solution for a small island where you don't have a grid as backup. And this is, if I remember correctly, La Réunion, where Florian was for his honeymoon. Okay, and we also, a colleague of mine did a presentation where La Réunion was in the background, the border of the island was in the background, but I don't have this model right now. Okay, and yeah, so this is just a simplified model right now. So we really don't have a final backup in case. So usually you would have like a motor backup or something like this for the model, but that's currently not in here. But at least we have this water storage and the battery as backup, and they work for this particular day. And in case you have always enough wind or solar power and to always ensure that the upper tank is full or the battery is full to to come over the low wind gaps and over the night, where usually the sun doesn't even shine on La Réunion. I was told so. And then you can even try to run this configuration on an island where you are willing to accept that maybe for 2 or 3 days in a year you are out of power for several hours, but you don't have to invest for an additional motor or something like this. I just start now the whole calculation, which is minute based right now. You see that the clock is running slower right now, and we are currently at 3 a.m. in the morning, and we have wind, which produces enough power. So the power demand for the whole island we set to be always like 1 megawatt. Of course, in a real model, you would also put in the power demand getting higher in the morning and higher in the evening, and with a low in the night, of course. But okay, we did it for simplicity like this. And we have some controllers in here, though these violet boxes are controllers, which ensure that for each point in time, the correct amount and the correct energy sources and drains are used. Because we have this static production of energy from the solar and the wind turbine, which simply produce or not produce, and we have a first splitter right here with the battery, which tries to fill the gap or take energy from the source, which was shortly 2.89 megawatts, and then the battery gets loaded in case there's too much power produced, but also the battery has a maximum of load which can get in there, and if the battery is full, the controllers will start pumping up water, and in case the energy production from solar and wind is too low, then at first hand the battery will be the battery also tries to fill the gap, and in case the battery is empty, the water tanks will be powered on and will produce the missing energy. So this is now a staged model. Of course, we could do it the other way around, but usually you put the battery as your first backup, because it has the least losses. Because usually if you use a water pump, I think you lose like 75% when you pump up and get the energy again. So it has a lot of losses. But okay, so.
Yeah, well, I think it was helpful because we saw lots of details here. I have an idea now. Let us finish up the official part, and I have another question. We can give another 10 minutes for those that have extra time. We can have another example either from the energy island or from the other stuff. I would like to finish here with our last slide for now. 1 second. We had that. Exactly. The yellow thing is what I wanted to say. We really invite you to challenge us afterwards. You have our contact data. You can just reach out and say, well, I saw very interesting things today from Tobias and Florian, but my problem is this one. Does it fit? Do I need EBSILON or SREPOS or something else? Let us have a talk about that. That is our invitation here. Second invitation, there will be more web seminars, and you can see each time we are changing and improving. Let us have your feedback, please, either now in the chat box, drop us an email afterwards. I think it was great. We had a good question here in between, so let us know how you liked it. And now I will finish here with our last poll, and then Tobias can show another thing in detail. I think that is very, very interesting, but unfortunately, the time is clicking like crazy. Time is ticking. So let us have a last question here, what the bonus presentation will be. Would you like to see something about this kind at the end here for the special round? Right. More renewables I can see. Tobias, I hope you have something there. Macro scripting, maybe we can have macro scripting for renewables. Let's wait another 5 seconds and then we will make that visible for everybody.
Okay.
1, 2, 3, 4, 5. That's it. Thank you very much. And Tobias, now maybe we can have another 10 minutes and I don't have to, interrupt you all the time. Sorry for that, but I know that some people are really on a strict schedule. So now, why don't we have, either you continue now with this focus with the energy island or something else to answer that question here.
I may.
Right. You can share again. I think I took it away from you. So the cameras. But yeah.
Okay. I try to share. I use another solar model which maybe has all 3 parts in it, because this is a model which meets the EU standards from like 15 years ago, I think it was, where the EU promoted models mostly in the southern of Spain, which produced more or less exactly 50 megawatts of power. And we have here like a small model of one of those plants which use a trough system. Those are models we developed together with the German Aerospace Association, and this is only so we have, maybe I go in here, so you may think we only have 2 rows of troughs in here, but not. That's not the case. So we have 2 lines of 4 troughs. If I go up here, and we have like a splitter and a header component for those trough systems. And the splitter, we have, all in all, we have 78 or 2 times 78 trough rows with 4 troughs. And we have like the trough we're now seeing, or we're calculating, is the 39th trough in this row. So we're calculating, of course, the mass disturbance over the distributing header, and also the pressure drop over those. And by using this technique, we can quite closely model the whole field by only calculating 2 rows of troughs in the system. So, again, we use the tank system. So we have a hot tank and a cold tank. I think this uses a molten salt tank in here as an intermediate heat liquid or thermal liquid. So the troughs are driven by this molten salt in here at temperatures at the inlet at roughly 300 degrees of Celsius, and at the outlet at almost 400 degrees of Celsius. Oh no, sorry, no, that's oil. That's oil on the outer, and we have in here. Sorry for that. And in here we have heat exchangers which can put the heat from the oil to the molten salt, and the molten salt is only circulating between those 2 tanks. Okay, sorry for that. And and for the fossil part, we also have an additional heat source in here, which is simply a conventional burner, a duct burner with some heat exchanger and exhaust gas, and this will be switched on in case there is heat missing, or also during the night to keep the oil warm enough, or to speed up in the morning the startup process. And
I'm sure you could limit the use of, annual percentage of gas compared to sun, because I remember that this was sometimes relevant for the permissions that you need to have such a plant.
Yes.
Okay,
okay, and here again, we have a test a day, which I can run, which is this is in 1 hour steps. I think it runs very fast. Okay, now we've calculated a whole day, but we also have models for whole years, and we have, for example, we have here a result which sums up the megawatt hours produced by the field, and we end up in the day we have produced roughly 13.6 megawatt hours with this field. And we can also switch to the whole year data. Okay, this is quite old, from 1988. We got weather data for this region, and okay, I can start it. It runs, and you see it calculates quite fast, but I think it takes roughly half an hour to calculate the whole year. Okay, so it's faster than Florian's model, but okay, sorry, switched it down. And on the water steam cycle, we have like a usual water steam cycle with I think a two stage or two pressure steam turbine, and we have like a two-stage transmission from the heat from the oil lines to the water cycle. So we have a preheater and verdampfer.
Evaporator.
Evaporator. Thanks a lot. We have two streams of preheater, evaporator, and superheaters. And I will stop it right now to show you some of the data that we come in with. Okay, let's go back to our. So we have 245 degrees at 101 bar. Okay, that's pretty hot and pretty high pressure. And at the preheating, we go to 308 bars, and then we are 311 degrees of Celsius. And after the preheater, we go up to 371 degrees with a slight pressure drop from 101 bar to 100 bar. So we are not in. So we still have evaporation in here, yes, of course. And this is still, you can always look, if you don't trust me, I think we should still see that the steam content is still 0, so we still have water in here. And I think that it's so pretty hot in here because the preheating is down here, of course. So we go into the preheating with 6 bars and 160 degrees. So.
Well, Tobias, I think it's pretty interesting because everybody is still sticking around. It's very impressive. Maybe something similar like the solar tower or the PV would help them to see really like where we use EBSILON in the solar. I mean, for sure we understood you have the solar data somehow from the German Aviation Agency, or you have it already, but that can be used as an input then for very versatile project setups. And it seems to be very, very interesting. So it's great. Thank you all for being so active here. And so, thanks.
Okay, so we have also different models for solar energy. So we have a tower model which splits into the tower and the solar field. So we don't have the software or
for the design, right?
Yeah, we don't do the design of the mirror field, but we have interfaces to plug in data from which you can get from DLR and tell EBSILON how your solar field looks like, because therefore we have this specification matrices where you can plug in your field efficiencies with respect to the position of the sun. So here in degrees, the sun position and the efficiency of the solar field, and we have cosine efficiency and blocking, shading for the different configurations. And this is all data we get from the configurator from the DLR. And so you can use that and produce your matrices and plug them into Epsilon. And okay, those are now just the heat, the tower and the field. But on the back end here, you would again have like a storage system and of course the heat transfer to the water steam cycle and so on. And I think finally to go to the photovoltaic, I have to figure out what is, that's 137. So all you see right here is also on the DVD when you install it. Those are all example models that are shipped with Epsilon. And here we have a model for PV module, which you can also specify with a lot of values. And we have a large database of, I will open it, but so you see, I scroll down and it scrolls and scrolls and scrolls. Wow. I think we have like 20,000 different photovoltaic models in here. But the nice thing, if you search something, I don't know how it's called right now, or you go to Nanjing, whatever, and or Yunnan right now, and the list, gets very small, and you can select the photovoltaic system you're looking for, and then you can replace the data. And yeah, it's quite easy to select the photovoltaic system you actually want to use in your model. Yeah.
Is it right that there's a component for the sun that is actually a sun that you can add to your model?
Yeah, you usually have to add the sun. Though this is the sun right here, because the sun has different shapes. It has this shape, or a shape as a classic clock, or we also have like with date and time.
So in this model, you actually have two suns.
Yeah, we have two suns. So, yeah, so you can also use it on different planets, even on far away other solar models with two or more suns. No, the idea behind this is, of course, you can have different configurations fitting on different locations on this planet, and you can calculate them in one model, because you may have, they have different coordinates, because you not only use the sun for specifying the time information, you also specify the longitude and latitude of this, of your location, so it's your geo coordinates, and
but you can't change the weather in Bochum.
Yeah, I can't change the weather in Bochum, but on the other hand, you specify for each of those sun or solar dependent components, you specify an index up here, and this index then is specified. Okay, here is the index for the sun, for this sun, and when we look at the other one, it should be a 2 in here. Yeah, you see a 2 in here, and this one refers to the sun with index 2. And of course, Epsilon will warn you when you have two suns with the same index, or a component maps to a sun to an index that doesn't exist in your model. I think that's one of the other strengths we didn't mention at all of Epsilon, is it's really has a strong and good error signaling model, which shows you where in your model an error is currently.
You can trace back actually the source of every error you make or every mistake.
Okay, when I now delete this is a mass flow. The main mass flow is specified up here, and this is just a try, and I try to to calculate it, I get an error already in the input data, and it now shows me, oh, you have missing mass flows, and I can go, okay, we have missing mass flows on many lines right now, because I could specify the mass flow on any of those lines, but I know there is a mass flow missing, and when I re-enable the mass flow, so I just hit the undo button, it calculates again. And you could also get a very detailed error information if during the simulation something goes wrong, like a pressure drops to negative pressure, or mass flow reverses, or whatever, or the energy balance cannot be closed. Yeah, and also if you have overdetermination, so you can do overdetermination in your model, and then the model calculates. Oh no, Epsilon now doesn't allow me to paste because I'm in the demo model.
You know what? It's already 15 minutes over. It's so interesting and it's really amazing. Most of the people are still there. So I have an idea. Why don't we collect user stories, problems like, can I do this? Can I do that? And if we have a couple of those, we can maybe have another web seminar soon. I think Tobias will be available for those things on a short notice, because that is his daily business there. Let's collect that, or even have a private talk if there is something very specific. That would be my idea. And therefore, let's call it a day for today.
Yeah.
Give us feedback, please. We always try to fulfill your needs the best here. This is for you. You should learn something. But I think, considering those polls that I found them very helpful. We could focus on what you wanted to know. I hope you got the answers. You got some ideas, and maybe a special extra for those that do not have Epsilon yet. If you want to try it out, what you saw here today, we can even give you like a trial version for 2 weeks, something like that, just to check it out, how that works in detail. Get in touch, and I will talk to our colleagues there in Zwingenberg and make sure you get everything that you need. So, well, for now, Tobias, thank you very much. Thank you, Florian. Sorry that I had to slow you down once in a while, but yes, let's all go back to our daily stuff. And I hope to see you all again next month. And please give feedback here or in an email. It would be great. And yes, thank you all. Have a good rest of the day.
Goodbye.
And goodbye.
Stay healthy.
Bye. Thank you.
Bye.